Hello friends, I welcome you in lecture number 9 on first order ordinary differential equations. In previous lecture we have discussed what is exact differential equation and how to find out its general solution. In this lecture we will see if our differential equation is not exact, then how to convert it into exact differential equation. So first we recall that if we have differential equation in this form m dx plus n dy equal to 0, then this differential equation is exact if partial derivative of m with respect to y and partial derivative of n with respect to x are equal, and if this differential equation is exact, its general solution is given by this formula: integral of m dx considering y as constant, and here we consider those terms of capital N which do not contain x, terms of n not containing x. So this is going to be function of y which we integrate with respect to y equal to constant of integration. So this was the formula for general solution of exact differential equation. Now suppose our differential equation 1 is not exact, then this condition will not be satisfied. So in this case, if we can find out some function of x and y, say capital F of xy, such that after multiplying this equation with this function capital F, the new equation becomes exact. Suppose I multiply equation 1 by capital F, then I will have f into m dx plus f into n dy equal to 0. So suppose there exists a function of x and y such that after multiplying equation 1 with this function, the new equation becomes exact. Then this function is known as integrating factor. Capital F is known as integrating factor of equation 1, and the resulting equation 2 becomes exact. So we can solve this exact differential equation using this formula. Instead of m, we will write down this f into m, and here we will consider terms of f into n not containing x. Now the question is whether integrating factor exists or not. So there always exists an integrating factor, but there is no general method for finding out integrating factor. So we will discuss some different working rules for finding out integrating factor, and differential equation may have more than one integrating factors. In fact, there are an infinite number of integrating factors for the given equation. So with this in mind, we discuss that how to find out integrating factors, what are the different working rules, and here we have written the definition of integrating factor. We just go through this. If an equation of the form m dx plus n dy equal to 0 is not exact, then it can always be made exact by multiplying by some function of x and y, say capital F of xy. Such a function fxy is called an integrating factor. For integrating factor we will shortly write I dot f. So as I discussed, there is no general method for finding integrating factors, but we can have some working rules for deciding integrating factors. So we discuss them one by one. In this lecture we will discuss working rule 1 to find out integrating factor. Suppose the differential equation m dx plus n dy equal to 0 is not exact. So if this equation is not exact, then del m by del y and del n by del x will be different, so they are not equal. So if we take difference of these two, then it is non-zero. So here we consider difference of del m by del y and del n by del x, and we divide this difference by capital N. So if we find out this difference divided by n, and whatever we find out, that quantity is a function of x only. If del m by del y minus del n by del x divided by coefficient of dy, which is capital N, equal to function of x only, then we will remember that integrating factor is given by e to the power integral of this function with respect to x, and then we will multiply our equation by this integrating factor and our equation will become exact. So this is the first working rule to find out integrating factor. If del m by del y minus del n by del x over n equal to fx, here we have function of x only. It can be constant also, because constant can be considered as function of x. So if this quantity is a function of x, then integrating factor is given by this formula. So if you obtain function of x, then use this formula to find out integrating factor. If you are not getting function of x only, then this rule will not work and we have to think for another rule. But today we are considering examples related to this rule 1. So we start with this example. First we check whether this differential equation is exact or not. For that we compare with m dx plus n dy equal to 0. Comparing given equation with m dx plus n dy equal to 0, we have, so capital M is coefficient of dx, which is x square plus y square plus 3, and capital N is coefficient of dy, which is minus 2xy. So now we check the condition for exactness. Del m by del y, we consider x as constant, so derivative of x square is 0, derivative of y square is 2y, derivative of 3 is 0, and partial derivative of n with respect to x, so we consider y as constant, so minus 2y is constant, derivative of x is 1. So we can see these two are different, therefore del m by del y is not equal to del n by del x. Therefore given differential equation is not exact. So we now try working rule 1. We find out, we see what we get for this quantity. So we take difference of del m by del y and del n by del x, and we divide this difference by capital N. Del m by del y is 2y, del n by del x is minus 2y, and capital N is minus 2xy. So this is going to be 2y plus 2y, negative negative positive, divided by minus 2xy. So we can cancel out this 2y with this 4y. So here 2 will cancel out, y will cancel out, and we obtain minus 2 by x. So we can see this is function of x only, equal to say fx. So if this quantity is a function of x, then we will remember that integrating factor is given by e to the power integral of function of x dx. So fx is minus 2 by x dx integral of minus 2 by x is minus 2 log x, and using property of logarithm we can rewrite minus 2 log x as it ln x raised to minus 2, but this is nothing but x raised to minus 2. So therefore integrating factor is x raised to minus 2. So we have seen first step was to check whether equation is exact or not. So we find that equation is not exact, so we try to find out this quantity which turns out to be function of x. So using the formula for integrating factor we obtain this integrating factor. So now next step is we will multiply given equation by this integrating factor. Multiplying given differential equation by integrating factor x raised to minus 2, we get so x square plus y square plus 3 dx minus 2xy dy. So we write one more step. We multiply x square plus y square plus 3 dx with x raised to minus 2, and we have minus 2xy, that also is multiplied with x raised to minus 2. So we check again, x square plus y square plus 3, it is multiplied with x raised to minus 2, and minus 2xy is multiplied with x raised to minus 2. So now we simplify, we take x raised to minus 2 inside the bracket. So we have x raised to 2 minus 2 0, that is 1, plus y square times x raised to minus 2 plus 3 into x raised to minus 2 dx minus 2 y is there, x raised to minus 1 y dy equal to 0. Here x raised to 1, x raised to minus 2, so that is x raised to minus 1 and minus 2y as it is. So after multiplying we obtain this differential equation, and this is always exact. We don't have to check whether it is exact or not, and we denote coefficient of dx by, say, instead of m we can use m dash. M is already used, so m dash equal to 1 plus y square x raised to minus 2 3 x raised to minus 2 and capital N equal to minus 2 x raised to minus 1 y. If we wish we can check whether this is exact or not, but you don't have to write or you don't have to prove that this is exact, because after multiplying integrating factor it will always become exact. Suppose we try to check for our satisfaction, then first we differentiate m dash with respect to y. So derivative of 1 is 0, x raised to minus 2 as it is, derivative of y square is 2y. So we have 2y x raised to minus 2. Derivative of this is 0 with respect to y. And we find out here I have to use n dash. N is already used for given equation. Del n dash by del x. So here minus 2y constant, derivative of x raised to minus 1 is minus 1 x raised to minus 2. So here negative negative positive, and we have 2y x raised to minus 2. So we can see both are same. So this differential equation which we obtain by multiplying with integrating factor is exact. So this is just for our satisfaction. We don't have to show that resulting equation is exact. It is always exact, because by the definition of integrating factor we can write directly which is exact, and now we find out its general solution. So therefore the general solution is The formula is same, but instead of m we have m dash, so we write integral of m dash with respect to x considering y as constant. Here we write terms of n dash free from x, or terms of n dash not containing x, integral with respect to y equal to constant of integration. Now in n dash there is only one term and it contains x, so there is no term in n dash which is free from x, and we integrate m dash with respect to y. So therefore m dash is 1 plus y square x raised to minus 2 plus 3x raised to minus 2. We integrate with respect to x considering y as constant, and there is no term in n dash which do not contain x, so we write 0 here equal to c. So now we integrate with respect to x. Integral of 1 with respect to x is x, y square constant. Integral of x raised to minus 2 is x raised to minus 2 plus 1 divided by minus 2 plus 1, and here also same thing, 3x raised to minus 1 divided by minus 1 plus 0 equal to c. So we rewrite all these things. This is x square minus x minus y square by x minus 3 by x equal to c, and this we can rewrite by multiplying with x. So we have x square minus y square minus 3 equal to c into x, where c is arbitrary constant. So this is the general solution of given equation, which was not exact, but we made it exact by multiplying with integrating factor. So this is the example which explains how to find out integrating factor if this condition is satisfied. If del m by del y minus del n by del x divided by n is function of x only, then integrating factor is given by this formula. We consider one more example. Solve the initial value problem. 2 sin of y square dx plus xy cos of y square dy equal to 0, and condition is when x equal to 2, y is square root of y by 2. So first we write down given differential equation is 2 sin of y square dx plus xy cosine of y square dy equal to 0. So we give this number 1 so that we don't have to write down given equation every time. Okay, fine. So now here if we compare with m dx plus n dy equal to 0, m is coefficient of dx which is 2 times sine of y square, and capital N is coefficient of dy which is xy times cos of y square. So now we check the condition for exactness. Partial derivative of m with respect to y is 2 constant, derivative of sine is cosine, and by the chain rule we have to write in the multiplication derivative of y square which is 2y. So this is 4 times y cosine of y square, and we find out what is del n by del x. So here del n by del x, in del n by del x y is constant, so we have y cos y square constant, derivative of x is 1. So we can see del m by del y and del n by del x are different, is not equal to del n by del x. So therefore equation 1, that is given equation, is not exact. So now we try to find out this quantity del m by del y minus del n by del x over capital N. Del m by del y is 4y cosine of y square minus y times cosine of y square divided by n, which is xy cosine of y square. So this is 4 times y cos y square minus 3 times minus 1 time y cos y square. So 4 minus 1, 3 times y cosine of y square divided by x times y cosine of y square. So y cosine of y square will cancel out and we are left with function of x only. So here also we can use working rule 1 to find out integrating factor. So we have integrating factor equal to e to the power integral of fx dx, which is here integral of 3 by x dx, which is equal to e raised to 3 times log x dx, log x. Integral of 1 by x is log x. This we can rewrite as log of x cube using property of logarithm. So we have integrating factor equal to x cube. Now the next step is multiplying given equation by this integrating factor. So we have given name integrating, we have given equation is multiplying given equation, which is considered as equation number 1, multiplying equation 1 by integrating factor, we obtain. So we write the resulting equation. We multiply equation 1 by x cube. Integrating factor is x cube. So this is going to be 2x cube sine y square dx. 2 times x cube sine of y square dx plus coefficient of dy was xy cos y square. So that is multiplied with x cube. So we have x raised to 4 y cos y square. X raised to 4 y cos y square dy equal to 0, and this is always exact. We don't have to check it, which is exact. With we consider coefficient of dx as m dash, which is equal to 2x cube sine of y square, and n dash equal to x raised to 4 y cosine of y square. So now this is exact differential equation. So we find out its general solution using this m dash and n dash. So therefore the general solution is integral of m dash with respect to x considering y as constant plus terms of n dash not containing x, terms of n dash not containing x, integral with respect to y equal to constant. In n dash there is only one term and it is containing x, so this quantity will be 0, and we integrate m dash with respect to x. M dash is 2x cube sine y square. So therefore 2x cube sine y square sine of y square dx. Here we have to consider y as constant. There is no term in n dash free from x, so we write 0 equal to c. Here y is constant, so 2 sin y square is constant. Integral of x cube is x raised to 4 over 4 equal to c. And we can see here 1 2 will cancel out, and we have x raised to 4 sin of y square divided by 2 equal to c. So this is the general solution of given differential equation. Now we use initial condition to find out particular solution, and initial condition was y of 2 equal to square root of pi by 2. That is, when x equal to 2, y is square root of pi by 2. So we use this initial condition in the general solution. So using y of 2 equal to square root of pi by 2. Okay, this means that is at x equal to 2, value of y is square root of pi by 2. So using this in equation 2, using this in 2, we obtain, so we will put x equal to 2 and y equal to square root of pi by 2. Here we have y square, so y square will be pi by 2, and we put x equal to 2, so we have 2 raised to 4 sin y square is pi by 2 divided by 2 equal to c. Sin pi by 2 is 1, and here 1 2 will cancel out, so we have 2 raised to 3 equal to c, that is c equal to 8. So we substitute value of c in equation 2, and we will obtain the solution of given initial value problem. So therefore the solution of given initial value problem is x raised to 4 sin y square divided by 2, x raised to 4 sin of y square divided by 2 equal to constant, which we have obtained as 8. Here we put c equal to, here we put c equal to 8. Left hand side is x raised to 4 sin of y square divided by 2. So therefore the final solution of given initial value problem is x raised to 4 sin y square equal to 16. So in this way we can find out general solution of differential equation which are not exact by using integrating factors. But remember, there is no general method for deciding integrating factor. We will discuss some working rules to decide integrating factors. So if they work, then you can apply this method. Otherwise you have to think for another method. So this is all about today's lecture. I hope you like this lecture. Thank you very much.